We are currently producing scientific data at a pace that defies human observation. Between ab initio simulations, massive AI training sets, and emerging quantum platforms, researchers generate millions of distinct calculations every single day. But an isolated number sitting on a server has no inherent scientific value. Without knowing exactly how that number was produced and the specific evidence supporting it, we cannot determine what it actually gives us the right to claim. Take a calculated crystal formation energy. As it moves through high-speed digital pipelines, it is compressed and reformatted, stripping away the methodological context until only a naked value remains. When algorithms summarize this data for reports or AI models, the vital nuances vanish. The margin of error, the hardware calibration, and the contradictory measurements are all quietly erased. Blindly amplifying this unclassified data allows automated systems to broadcast definitive conclusions that the underlying evidence simply cannot support. In 2003, Stefano Cartarolo and his team pioneered DMQC, data mining of quantum calculations. Their goal was to extract structural prediction rules from massive libraries of ab initio results. Independent researcher Jean-Sebastien has proposed an evolution of this concept. He reframes DMQC as an admission layer, a strict software protocol that governs the transition from a raw result to a publishable claim. The research software FNP-QNN serves as a prototype for this checkpoint. Before any data point is integrated into a public interface, it must pass through this digital customs chamber. FNP-QNN exists to test software logic on synthetic fixtures. It does not run live density functional theory calculations, nor is it a demonstration of hardware-based quantum advantage. The software enforces a single requirement. Every calculation must be merged with its provenance, its uncertainty, and its contradictions before it is allowed to reach the public. Inside the admission chamber, a triage system routes incoming data. Admitted data is surgically bound to permitted claims. Results with high uncertainty enter the suspended state, preserved but blocked from promotion. Anything failing hard invariance, like missing provenance, is rejected and blocked at the source. Forcing the scientific pipeline to use these three states prevents unverified calculations from masquerading as absolute published facts. Real-world scientific data is messy. A single material might show favorable energy levels, but highly unstable growth patterns, leaving researchers with attributes that simultaneously support and contradict a single hypothesis. To manage this, the system explores frameworks like plithogeny and nutrosophy. These models attempt to preserve and map multi-attribute contradictions rather than averaging them into a single misleading score. In pilot benchmarks, scientific honesty won out over complexity. Simpler Boolean rules tied to strict provenance actually outperformed the more complex plithogenic logic in accuracy and recall. The tool Cynthia is used here strictly for conceptual and lexical traceability, ensuring that turns and evidence remain linked through the process without acting as a scientific authority. True rigor involves designing systems that are allowed to fail their own hypotheses, prioritizing auditable logic over opaque complexity. The modern research landscape is defined by massive cloud workflows, endless data lakes, and centralized databases like Nomad. Hoarding exabytes of results we cannot reliably interpret creates an unsustainable burden on energy and computation. This is the looming classify never era. Computational science advances now through the construction of systemic mechanisms, tools that bind every data point in a database to its specific origin and its physical limits. The DMQC admission layer is an invitation to the software community to adopt strict claim governance before technical amplification outpaces our ability to understand the results. Classifying results at the source tethers technical speed to human comprehension, preventing the acceleration of calculation from becoming the acceleration of error.